Hello everyone, I'm Pensheng Li. Today I want to share my work. My topic is exploring the uncertainty in chip-based electricity consumption of EVs with the real-world big data from 100% electrification of bus network in Shenzhen, China. Our presentation contains 5 parts: background, literature review, data collection, model development, results, and discussion. Currently, in order to encourage the transportation electrification, more and more cities are replacing diesel-powered public buses with electric buses. This is because electric buses are classified as zero-emission vehicles and being more energy efficient in urban areas. There are a lot of advantages of EVs, including quiet, comfortable due to the lack of motor vibration, and braking energy recovery, being more energy efficient than diesel-powered buses, and being locally emission-free due to the fossil fuel savings and the reduction of greenhouse gases emission. Currently produced vehicles have limited battery capacity, and their efficient operation requires a strategy for planning charging stops in the course of daily operation. There are 3 main charging technologies: low power charging through cable and plug-in, high power charging through conductive charging, and fast charging through inductive charging. Charging strategies include opportunity charging, depot charging, and a combination of opportunity and depot charging. An accurate energy consumption estimation tools enables the optimization of the placement of charging stations, times for charging in the transportation networks, and the modification of battery schedules. In literature review, there has been a lot of studies in the calculation of electricity consumption of EVs. Existing studies mostly use 2 approaches to determine the electricity consumption of EVs for terminal-to-terminal trips. The first is sum of rule. It assumes that the linear relationship between the electricity consumption of EVs and their trip length. Although this approach is very simple to estimate the electricity consumption, it doesn't take into account the impact of other influencing factors on electricity consumption. Hence, there would be a less accurate electricity consumption estimation through using this approach. The second is the physics-based models. The range of models for electricity consumption covers a wide spectrum of drive description approaches. There are complex kinematic models of vehicle movements, route-based scenarios of energy consumption, models incorporating scenarios of energy consumption, models incorporating models incorporating characteristics of driving styles, environmental variations, and vehicle construction related factors. These models require complex measurements of variables used for the description of elements of the models, and a reference to produce a detailed physical modeling of this. However, none of existing studies consider inherent variability in the real-world operation. So here, we developed a chip-based electricity consumption prediction model based on big data through neural network. The raw data in this study originated from the electric bus data from 1,024 electric buses consecutively connected from January 1st to May 31st, 2019 in Shenzhen, China. The data including the bus ID, the GPS time, the accumulative mileage, the current speed, and the current state of charge, and the GPS coordinates. All of them are recorded every 10 seconds. The right figure shows the geographic heat map for the traces of the connected EV data. Our study is to research the EV's electricity consumption for trip-based for terminus to terminal trip. Hence, for the purpose of analysis, the connected row dataset was first aggregated and converted into terminal-to-terminal trips records through splitting the row data based on the positions of the two terminal stops, then the data for the departure time of the day, departure day of the week, trip length, average travel speed, driving direction, and the electricity consumption for terminal trip was obtained based on the processed data. Then, through a time-consuming manual search, the baseline information corresponding to each terminal record was determined. And the data about the number of bus stops visited and the number of traffic lights passed, which were covered in the baseline information, were matched to each record. And then we get the pre-processed EB data. The variables and their types and their measurements are listed in this table. Firstly, we should know the characteristic of the bus network. From the left figure, the median bus trip length is 12.7 km, and the mean value is 15.9 km. The distribution is quite wide with a standard deviation of 9.2 km. From the right figure, the median number of the bus stops reaches up to 1.8 stops per kilometer. In other words, the median distance of two adjacent visited bus stops is 556 meters. The standard deviation is 0.51 kilometer. Then we conduct the data analysis. The left figure presents the relationship between the fifth, the median, and the 95th percentiles of trip-based electricity consumption observed for each bus line and trip length. The electricity consumption appears to be roughly proportional to the trip length. However, with the trip length over 30 km, the energy consumption rate has a different performance from that of the trip length below 13 km. This can be attributed to the fact that when a trip length exceeds 30 kilometers, it indicates that the EBs usually shuttle between the suburbs and the urban area. In general, there are a lot too much traffic congestion and lower ridership during the trip between suburbans and urban areas. So the traffic conditions are much better and the mass of EB are much smaller, which result in less idle duration time and further higher electricity efficient. The right figure compares the electricity consumption per kilometer for different driving directions on the basis of each departure time. From 6 to 9 a.m., the median electricity consumption for routes driving to and off urban areas are similar. However, from 10 a.m. to 9 p.m., the median electricity consumption for routes driving off urban areas is higher than the routes driving to urban areas. This difference reaches a maximum of 0.16 kilowatt-hour per kilometer during the peak evening hours. Hence, the driving direction is another important influencing factor affecting the trip-based electricity consumption of EVs. The left figure compares the electricity consumption per kilometer of EVs for the different departure times. During peak hours, the electricity consumption per kilometer approximately 1.19 kilowatt-hour per kilometer is relatively higher than during other time period. This is attributed to the fact that there are more passengers on the buses, which increases the mass of the vehicle, and the road congestion is heavier at those times, which reduce the travel speed and increase the amount of idle time. The right figure compares the electricity consumption per kilometer for different days of the week. The electricity consumption on weekdays displays a similar pattern, as does the electricity consumption on weekends. However, there is a significant difference in the electricity consumption between weekdays and weekends. The electricity consumption on weekdays is considerably higher, owing to the higher number of passengers commuting to and from work on buses. In comparison, on the weekends, there is not as much travel demand, which could result in reduced travel pressure and lower electricity consumption. Hence, the differences in the values of variable related to route characteristics and dynamic traffic conditions have an impact on electricity consumption estimates. Therefore, all of these variables are included as input parameters. In this study, a three-layer BP neural network is built. Cross-validation is performed for the selection of the parameter. After minimizing the mean absolute percentage error in the process of optimization, the number of neurons in the hidden layers can be determined, which is set to 10 in this study. To better analyze the actual prediction performance of this neural network electricity consumption prediction model, the prediction results need to be evaluated and analyzed. In this study, the following performance accuracy indicators are adopted: MAE, MAP, and RMSE, which are given by as follows. Applying the neural network's electricity consumption prediction model to this dataset, the predicted results are obtained, shown in the figure A, and the relative error on the prediction for this trip-based electricity consumption and its distribution can be seen in figure B. The figure B shows the average relative error decreases for trips with a higher quantity of energy consumed, and the median and the mean relative error is 0.98 percentage and 4.53 percentage respectively, excluding outliers. The 5th and the 95th percentile of relative error are negative 27.48 percentage and 49.09 percentage respectively. Further, according to the prediction accuracy indicators, the values of the MAE and MAPE and the RMSE are 2.36, 17.22 percentage and 3.1 TRF respectively, which could indicate that this neural network electricity consumption prediction model performs very well. To have a deep understanding to identify which parameter have the greatest influence on the prediction results, a sensitivity analysis is performed in our model. Some input variable both departure time of day, departure day of week, driving direction could not be quantified, so sensitivity analysis are performed on 4 different conditions. For the sake of brevity, every other single input variable is fixed to its median value, corresponding to the base cases. The high and low cases corresponding to a variation of positive 10% and negative 10% from the base value for each variable respectively. From the results, it can be observed that the variable with the highest impact on the electricity consumption is the trip length under the 4 different conditions. Under the conditions C to D, its influence is more obvious than other 2 variables. The impact of average speed is also worth attention. With the average speed increasing, the electricity consumption decreases, only confined to the average on-trip speed of no more than 25 kilometer per hour. As the average speed of terminal-to-terminal trips in our experiments are no more than 25 kilometer per hour. Further, the influence of the number of bus stops and the traffic lights are also cannot be neglected. The electricity consumption also increase with more bus stops and traffic lights. So, in summary, our consumption, our contributions can be summarized as follows. Neural network electricity consumption prediction models was proposed, and we considered 6 influencing variables, and our model was validated by real-world electric bus data from a 5-month consecutive collection in Shenzhen, China, comprising 1025 EBs. And also, sensitivity analysis is performed to understand the impacts or influencing factors on the prediction results. So the proposed prediction model in this study can serve as a basis of scheduling optimization of large-scale electric bus fleets and the optimization of the location of charging infrastructures. So that is all about our work. Thank you for your listening.